Hey there, welcome back to the channel. So, in the previous video, we covered from 12.1 to 12.6, which is references and value references about R value. We did not cover R value references. Like it's in the next chapters. It's not, I guess, in this chapter itself. But yeah, we have covered L value references. So let's get back into it. So this is about pointers. I am kind of comfortable with pointers, you can say. So I'll be skipping most of the part over here. I've covered this subchapter yesterday itself, but I'm just going to skip over it. Okay. So this is address, this is dereferencing. Yep, covered this also. A pointer to an int value, cool. This is the L value reference. Ampersand sign can have, okay, yeah, this also. So when you declare it like this pointer to is not a pointer. Like the pointer to it's written, but it's not a pointer. It will be declared as an int because this is supposed to be this is supposed to go with the identifier. Yep. Instead of saying the variable name, I said identifier. That makes me sound cool. So yeah, we initialize with this way. It's fine if we don't initialize it right away. It becomes a null pointer. Cool. Yeah, this is the dereferencing part. The pointer is a block of uh, it's a block of whatever you can say that whatever is the architecture of your not architecture, but what is it called? What is it called when I guess architecture itself, right? Yeah. If most probably you have a 64-bit architecture, so your pointer will also be of 64 bits, which is 8 bytes. Yep. So so this is and I yeah, pointers can only be of the same size. Int pointer can only be a pointer to a int. Int pointer cannot be a pointer to a d, which is double. It's not okay. Not cool, bro. You also cannot do this, so you also cannot just directly give it an address. I think there might be a reason to it. I'm not sure why, but okay. I don't think this makes kind of sense. There might be a lot of stuff inside the pointer itself, like how it is managed and all. But okay, cool. Pointers and assignment. Uh, I think I've done this point to, yeah, as equal to 6, pointer is equal to and y, change pointer to pointer to y. Yeah, yeah, cool, cool, cool. Yeah, this is just going to change stuff. Pointer into y. Now this points to address of y. So this is address. So this pointer now points to y. So okay, so there is a variable x and there is a variable y. Initially, the PTR points to x and then afterwards it is pointing to y. So when we print it the second time, when we dereference the pointer second time, it will change what the stuff is. When we are doing it with the reference, it was not. It was changing the value of the first variable itself. But okay, cool. Okay, yeah, taking the address, yout x, 5, 5, 5, 5, dereference x equal to 6, 6, 6. Yep, cool. Okay, when you use a pointer without a dereference, we are accessing the address held by the pointer, modifying this pointer is equal to and y changes that what the pointer is pointing at. When you dereference a pointer stop asterisk PTR, we are accessing the object being pointed at, modifying this changes the value of the object being pointed at. Cool. So pointer behaves much like L value references. Yes, they do. Uh, but I've yet to see something interesting. I think R value references might be a bit interesting, but I have to take a look at it. Okay, so yeah, X. Yeah, okay, that's the output. So yep. So this is a reference of X. So this is X itself. Pointer points to, yeah, this is the address. Cool. So X, so this will be 555. Reference, when reference is equal to 6. So now X will also be 6. Reference is definitely 6. And pointer, this will be 6 also. Boom, cool. And then we are, yeah, this will also be the 777. Because dereferencing a pointer and changing its value to 7 will also change the value of the original identifier, which is the original memory block. It also, and since we are changing it over here, this will also change, which is the reference. And yeah, then the reference pointer will also change. Cool. Reference will also be wrong. Oh, okay. I should read these. There are some differences between pointers and references worth mentioning. References must be initialized. Yeah. References need to be initialized and they cannot be changed. References are not objects. Pointers are. Okay, okay. Pointer is an object. The references cannot be resetted. Yeah, that's what it is. You cannot change what the reference, like who the referent, you cannot change who the referent of the reference was. Cool. It cannot be resetted, which is we cannot change it. Pointers can change whatever they're pointing at. References must always be bound to an object. I'm audible. Audible, audible, audible. Recording, recording, recording. Cool. Pointers can change what they are pointing at. References must always be bound to an object. Yeah, pointers can point to nothing. We'll see an example of this. Null or null pointer or whatever. References are safe. What does it mean? Outside of dangling references, pointers are inherently dangerous. We'll also discuss it in. Hey, don't do that, no one, boy. Pointers are cool, bro. References are safe. Yeah. And then you're saying outside of dangling references. Guess what? Pointers are also not safe when we are talking about dangling pointers, right? The address of operator returns a pointer. The address of operator returns a pointer. Okay. It's worth noting that the address of operator doesn't return the address of its operand as a literal, as C++ doesn't support address literals. Instead, it returns a pointer to the operand, whose value is the address of the operand. In other words, given variable int x, and x returns an int pointer holding the address of x. Okay, so it is not directly returning an address literal. It does not support address literals. Which language does support address literal? Which programming language supports address literals? Let's take a look. Sorry. So this is address programming language. I don't care about it. What? Is that possible? What? Huh? Okay. Let's try. So by the way, I'm not doing it purposefully. I just wanted to do it quickly, you know. So int a is 10, let's say, and then let's see. Yeah, just temporarily let me see what an example address looks like, you know. So this will be this will be address. Okay, let's take a look. Let's see. Let's see. Yeah, okay, so this is what it looks like. If I go over here, okay, I know I'm not going to get the value 10. I'm just giving it an example address. Okay, I know I'm not going to see a value 10 because virtual memory is different and physical memory is different. Okay, I know that stuff. Okay, chill. So I should, yeah, B. And I also want to take a look at what dereference to B looks like. Let's take a look. There's a zero over there. Cool. So it does support it. Hmm. It's worth noting that the address of operator doesn't return the address of its operand as a literal, as C++ doesn't support address returns. But it say this over here then. It returns a pointer to the operand of whose value is the address of the operand, in other words, given variable int. Why does learncpv.com say this then? Okay, the confusion here comes from the difference between address literals and pointer values. Hmm, C++ does not support address literals in the strict sense as some low-level languages like assembly do. That is, you cannot write something like int pointer this and expect it to return a literal address in the same way you would write a number like fi or hello. But it worked. Okay. If it does not support, then this should not be possible. Okay. Okay. And then I'm going to do, okay, it might corrupt some very, not a big deal. Std out, and then I'm going to do this again. This should, if it shows, okay, segmentation form. Cool. Because it's not in our memory. Okay, cool, cool, chill. Wait, okay. I know this is not valid, but I was just checking, can I do that? Okay, cool. So, okay, x4 should see out type ID x dot name. Okay, they should return int. Yeah, cool. And type ID and x, which is int pointer. So, and ampersand x is not returning a literal. If it was returning a literal, then we might see something different, but it's returning int pointer holding the address of x. Boom. Sorry. In GCC, this printed I, int, and pi pointed to int instead. Okay, this printed I. Yeah, cool. Because the result of the type ID dot name is a compiler dependent, your compiler may print different stuff. Yeah, I think uh, the person uses Clang itself, so I should see the same output. I can just write 11, or even if I don't do it, I think this will work because I haven't used any kind of like fancy feature, right? Oh yeah, a direct list initialization. Yeah. Oh, okay. So they are using GCC. Oh, this is Visual Studio. Okay. The size of the pointers. Yeah, the size of a pointer is dependent upon the architecture the executable is compiled for. Wait, 17 minutes. A 32-bit executable uses 32-bit memory addresses. Consequently, a pointer on a 32-bit machine is 32 bits, 4 bytes. With a 64-bit executable, a pointer would be 64 bits, 8 bytes. Note that this is true regardless of the size of the object being pointed to. Yeah. Even if a integer is 4 bytes, its pointer will always be of 8 bytes. Cool. Let's take a look at this code. So char, this is 1 byte. Int pointer, yeah, and then int pointer, it is 8 bytes for me. Ints are usually 4 bytes, yeah. Long double, what is it? 8 or 12 bytes, okay, cool. Can I just do size double? Like, what, can I look at what size of long double? Is it possible? I'll zoom in a bit. I'll also add that to full screen. I should take it to the, yeah, this is good. Okay, compile it over here. Yeah, okay, it's 8. And also full screen, full screen. Cool. So regardless of the type of the pointer, pointer is always of the whatever the architecture is. 4, 4. In our case, this will be 8, 8, 8. But still, let me show you guys. No one's going to watch this video. Oh, why did I leave? No one's going to watch this video, but if you're watching this video, um, I would say do not watch this video. There is nothing informative in this video. If you're finding it cool that I'm dictating some stuff and trying out some stuff, that is okay. If you want to like keep looking at this or this is in your background, this is fine. But if you are actively looking at this video, uh, you know, work on something that you like. This video is a waste for you. Try out some other stuff. If you're already working and you're just slacking, that's fine too. But if you're actively looking at this video, try out some new stuff. Work on your own project. You know. Don't watch this video. Thanks for watching this video. I'm not going to end it, but okay. Yeah, this is because the pointer is just a memory address and the number of bits needed to access a memory address is constant. Yeah. So dangling pointers, much like a dangling reference, a dangling pointer is a pointer that is holding the address of an object that is no longer valid. Dereferencing a dangling pointer, example, in order to print the value being pointed at. Uh, Dereferencing a dangling pointer will lead to undefined behavior as you try to access an object that is no longer valid. Perhaps surprisingly, the standard says any other use of an invalid pointer value has implementation defined behavior. This means that if you can assign an invalid pointer to a new value, such as a null pointer, because it doesn't use the invalid pointer's value, however, any other operations that use the invalid pointer value, such as copying or incrementing any invalid pointer, will yield implementation defined behavior. Will it though? Will it though? Okay, let's try. Um, what can we try? Yeah, let's try malloc. Let's try new. But new doesn't return the pointer, right? Where can I get a pointer? Oh yeah, let's try this. So I have int main over here. So oh boy, I do not like this at all. Okay, so $3, boom, boom. Yeah, cool. Also do not. I used to do this. I used to write function like this, like the previous one, but I'm improving. So let's say I do int a 10, okay, and then I do this. I have a pointer, let's say int pointer p, and then I'll do this. And then I will say pointer. I wanted to do this, so that's cool. Uh, Pointer is equal to address of a, okay, and then if I do this, this should give me an error, but we'll see what it does. Oh, it works. So int was destroyed over here, but it's still working. So if you try to modify it, this should not work. All right? Yeah, it's still working. This should give me an error. Yup. Jingle bell, jingle bell. Hey, inner code A is created inside the inner block. This means A is a local variable with automatic storage duration. When the block ends, A should technically be destroyed and its memory should be freed. Pointer assignment inside the block, you can assign the address boom after scope or defined behavior. After the block ends, the variable A goes out of scope and is destroyed. At this point, the pointer P is left pointing to a memory location that no longer holds valid data. Accessing this memory because each memory has been relocated. However, in most cases, what you're doing might work because the memory where A was stored may not have been immediately overwritten or reused. However, this is still undefined behavior. Okay, let's force undefined behavior over here. So what happens is that when it goes into the stack, so let's try this. So if we do this, int int a equal to 1, int b equal to 2. Okay, so we are forcing stuff on the stack. Okay, this should work maybe, I'm not sure. I don't know how memory works, you know. Like I know some stuff, but yeah, it's still. Yeah. The fact that program seems to work and prints value is simply a result of the memory layout or how the compiler handles the unused space. Yeah, yeah, it's fine. Okay, cool. So any other use of an invalid pointer value has implementation defined behavior. This means that you can assign an invalid pointer a new value, such as null pointer, because this doesn't use the invalid pointer, however, implementation defined behavior. Yeah, cool. Dereferencing an invalid pointer will lead to undefined behavior. Any other use of an invalid behavior value is implementation defined. Hey, that's what they tried, you know. Let's go, cool. Y goes out of scope, star pointer, undefined behavior found dereferencing a pointer. Sorry. But it may not, as the object that pointer was pointing to it went out of scope and was disturbed at the end of the scope, leaving pointer dangling. The output should have been this, so dereferencing, so 5, 6, 6 again. What are some variables that hold a memory address? This can be uh, they can be dereferenced using the dereference operator to retrieve the value of the address they are holding. Dereferencing a while or dangling on null pointer will result in undefined behavior. Yeah, do not dereference a null pointer. Pointers are both more flexible than references and more dangerous. We'll continue to explore this in the upcoming lessons. Quiz time. What value does this program print? Assume short is 2 bytes and a 32-bit machine. Cool. Okay. Uh, okay, so I have 7. Pointer is address of 7. Cool. And value. This, so the output that I should see is, should I write it down? Okay, let's do it probably, you know. So first I will see this over here. For the value part, I will see 7. For the pointer part, I should see this again. And dereference, I should see 7 again. So this 7, this 7, this 7. Boom. Now the dereference part is 9. So the address should be the same. This 9, this 9. Pointer is now pointing to uh, what do you say? The other value. So the address. So pointer is now pointing to another int, another short, sorry. So it should point, it will have a different address as its value. And other value, so and other value is this. So this other value, wait, other value 3. And then pointer, okay. I should have wrote it down. But okay, I remember most of the stuff. I think I'm pretty comfortable with this. And in the end, size of pointer. Pointer is of what 32-bit machine, 4 bytes, and size of dereference pointer. Dereference pointer is short other value. So this is 2 bytes. So solution 7, 9, 3. Cool. 4 and 2. Yeah, I don't need the explanation. That's the size of it. The size of the short. Yeah, cool. What's wrong with this snippet of code? 45 in pointer and v1 initialize pointer with address of v1. Int v2 78 dereference pointer is equal to what? So this is dereferencing pointer. So we have dereferenced a pointer. We should give it a value. We should not give it an address. So this is what is wrong. We should directly give v2 instead of add. If line should be this. Yep, this correctly assigns the address. Yep, cool. Let's look at null pointers. Solving. Half an hour and we only completed one subchapter. So null pointer is pretty big, but okay, yeah, cool. We completed. So when we reach, yeah, Okay, I'm going to read. Should I read the joke? Okay, I'll read the joke after for like when I reach there. I'm going to read this subchapter for the joke. For the joke. Okay. In the previous lesson, 12.7, we covered the basics of pointers. Audible, 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 audible. Recording, recording, recording. Cool. In the previous lesson, we covered the basics of pointers, which are objects that hold the address of another object. This address can be dereferenced using the dereference operator to get the object at that address. Yeah. Let's look at the code. Yeah. Okay, okay, cool. Pointer, this. Yeah, cool. Null pointers. Besides a memory address, there is one additional value that a pointer can hold, a null value. Null value, I think it's 0xFFFFF, which is the end of the what is it? End of the memory, I can say, right? So if I do this, so if I do int pointer b is equal to null, and I do std cout, let's print b first. And then let's print address of B. How about that? Let's see what it looks like. Yeah, okay. This is 0x0. Wait, so what is I think this is the end of the address, right? Minus one or this? Oh yeah, yeah, yeah. Null pointer should be 0x0. Yeah, cool, cool, cool. That a pointer can hold a null value. A null value, often shortened to null, is a special value that means something has no value. Oh, by the way, the creator of null value creator quote. Yeah. They said something about Tony was, yeah, something related to this. So Tony Hoare, Null's creator, regrets his invention. They say that I call it my billion-dollar mistake. It was the invention of the null reference in 1965. At that time, I was designing the first comprehensive type system for references in an object-oriented language, Algol W. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. Cool. By the way, Algol W, I read something about that. Algol W inspiration for C++, something like that. Yeah, okay, cool. Okay, when a pointer is holding a null value, it means the pointer is not pointing at anything. Such a pointer is called a null pointer. The easiest we can do this, yeah. So this is a null pointer. Best practice valuation is your pointers to be null pointers if you are not initializing them with the address of a valid object. Because we can use assignment to change what a pointer is pointing at that is initially set to null can later be changed to a pointer at a valid object. So this is null into x, boom, 5. The null pointer keyword. Much like the keywords true and false represent Boolean literal values, the null pointer keyword represents a null pointer literal. We can use null pointer to explicitly initialize or assign a pointer to null. Hey, what is null then? Wait, do they cover this stuff in the sorry, do they cover this stuff in the future? Oh, they do not. Okay, so null versus null pointer. I need to know that, right? Why was it replaced? I know that in C++, 0x or null was replaced by null pointer in pointer-based applications. I'm just curious of the exact reason why they made this replacement. In what scenario is null pointer over null beneficial when dealing with pointers? Yeah, null pointer has types to null pointer t. Yeah, I knew that. It's implicitly convertible to any pointer type. Thus, wait, it's implicitly convertible to any pointer type. What does that mean? Thus, it will match std null pointer t or pointer types in overload resolution, but not other types such as int. 0 aka C's null bridged over into C++ could cause ambiguity in overloaded function resolution, among other things. Thanks to Caleb pointing this out. Yeah. Fourth, second, which one? Yeah, third one. Yeah, explain in short. A special type that we can only represent a null pointer. It represents a pointer that points to a no object or function. Usage used to initialize or assign a pointer to indicate that it does not point to anything. It is type safe and can be used with any pointer type, but not with non-pointer types like int. Was it possible in C? Is that what you're saying? Is okay. Not sure. See out. What was it? Printf. Incomplete pointer to integer conversion, initializing int with an expression of a type void pointer. Okay. It is type safe and can be used with any pointer type, but not with non-pointer types like int. Uh, okay. So if I do this, was that something that was possible in earlier C++? Was that what you're saying? So I'm not, as you can see, I'm not using. That's what. Wait, that's an error in C. Cool. What was it? Yeah, it's fine. So it worked. My God, dang. So you're saying I'm going to see a value of zero. Yup, it used to work. Array zero or void pointer zero, an integer constant that represents the null pointer. Purpose also represents a pointer that does not point to anything, but it's an integer constant and not type safe. Usage traditionally used before C++11, but less safe than null pointer, since it's just a integer. But C is able to recognize the error and not give a warning. Why didn't C++ adopt that too? In C, null is typically defined as void pointer 0, which is a void pointer type. Assigning null to an int in C results in a compilation error because void pointer, yeah, in C++, null is typically defined as 0 or this, but in C++, 0 can be implicitly converted. Ooh. But in C++, 0 can be implicitly converted to a pointer type, making it compatible with both pointers and integers. Let me get my phone over to this side and let me do this. Damn, damn, implicit conversion. Cool. C++ has overloading functions and none or zero can be used for both integer types here. Cool. So use null pointer, guys. Can be null pointer to initialize a pointer to be null. Yeah, okay. So I'll remove main.c, remove a.out. Yeah. So this should not give me. This will give me an error. Okay, let's see. So this should give me an error, but we'll check it out. Value of null pointer t. Wait, it was 8. I should see this in C++ reference, right? This site usually shows it in what since C++11. But when I'm not giving it any kind of instruction, the default is clang. So, okay. So directless initialization was introduced in C++11. So if I do this, yep, an error. I just don't get this. By default, when you compile without specifying C++ version, the compiler like Clang++ will default to C++98 on an earlier standard which doesn't have null pointer or monophysers. Why you are seeing this error? Null pointer in C++98 the keyword null pointer does not exist. The compiler doesn't recognize null pointer t either. That's why you're seeing the error cannot initialize a variable of type int with the R value of type stored null pointer t. The compiler doesn't know about null pointer because it's a feature from C++11 onward. Huh? This is not because null pointer is 100 pairs. Null pointer is a special null pointer in C++ and research. Okay, that null pointer is a pointer type. Why it works in C++ programming letter. Okay, I'm not. I don't think I'm going to get an answer. Just skip it. Not worth it. Some function null pointer. We can also pass null pointer to a function that has a pointer parameter. Yeah, cool. Cool. Use null pointer when you find a null pointer letter for initialization, assignment, or passing a null pointer to a function. Dereferencing a null pointer results in undefined behavior, much like dereferencing a dangling or um, let's see what dereferencing a null pointer gives us. Yeah, let's keep it. Let's see. Yeah. Segmentation fault. It's a null pointer differencing. Doesn't allow indirection of an operand of type void pointer. Okay, so for void pointer is not allowed. Yeah, cool. If this was, let's say, null, what would the reaction be? Segmentation fault. Cool. Much like dereferencing a dangling or while pointer leads to undefined behavior, dereferencing a null pointer also leads to undefined behavior. In most cases, it will crash your application. The following program illustrates this and will probably crash or terminate your application. Okay, don't harm your machine. Okay. Yeah, conceptually this makes sense. Dereferencing a pointer means go to the address of the pointer is pointing at and access the value there. A null pointer holds a null value, which semantically means the pointer is not pointing at anything. So, what value would it access? Accidentally dereferencing null and dangling pointers is often most common mistakes C++ programmers make and is probably the most common reason that C++ program crash in practice. Mm, yeah, cool. No, okay. Accidentally dereferencing null and dangling pointers is one of the most common mistakes, yeah. Whenever you are using pointers, you need to be extra careful that your code isn't dereferencing null or dangling pointers, as this will cause undefined behavior, probably an application crash. Checking for null pointers. Much like we can use a conditional to test Boolean values for true and false, we can use a conditional where a pointer has null pointer or not. Explicit test for equivalence. So 5, address, pointer, pointer is not null pointer, pointer is not null. Boom. Null pointer this. Null pointer is null if this is true and non-null if this is not true. But in this case, this is true, so we will see null. Boom. Yeah, okay. Similarly, pointers will also implicitly convert to Boolean values. A null pointer converts to Boolean value false, and non-null pointer converts to Boolean value true. This allows us to skip explicit. Oh, that's what we are doing over here. No, we are directly checking. So yeah, they could do this because null pointer, if it's no, null pointer, it will implicitly convert to a Boolean value of false. Cool. This is null. Cool, 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 cool. Conditionals can only be used to differentiate null pointers from non-null pointers. There is no convenient way to determine whether non-null pointer is pointing to a valid object or dangling pointer to an invalid object. Use null pointer to avoid dangling pointers. Above, we mentioned that dereferencing a pointer that is either null or dangling will result in undefined behavior. Therefore, we need to ensure our code does not do either of these things. We can easily avoid dereferencing a null pointer by using a conditional to ensure a pointer is not null before trying to dereference it. Okay, we can easily avoid dereferencing a null pointer by using a conditional. Yeah. If pointer is not null, then only you can print. Else, do something else that does not involve dereferencing pointer, print an error message, do nothing at all. But what about dangling pointers? Because there is no way to detect whether a pointer is dangling, we need to avoid having any dangling pointers in our program in the first place. We do that by ensuring that any pointer that is not pointing at a valid object is set to null pointer. That way, before dereferencing a pointer, we only need to test whether it is null. If it is not null, we assume the pointer is not dangling. Best practice, a pointer should either hold the address of a valid object or be set to null pointer. That way we only need to test. Okay, cool. Unfortunately, avoiding dangling pointers isn't always easy. When an object is destroyed, any pointer to that object will be left dangling. Such pointers are not nulled automatically. It is the programmer's responsibility to ensure that all pointers to an object that has been destroyed are properly set to null pointer. Warning, when an object is destroyed, any pointers to the destroyed object will be left dangling. They will not be automatically set to null pointer. That's what I read. Why are you repeating stuff? Gee. Legacy null pointer literals zero and null. In older code, you may see two other literal. Well, oh, I'm audible, 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 audible. Hello, 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 hello. Okay, both of these are working, I guess. But okay, I need to charge my phone. 53 minutes in. That's cool. So legacy null pointers. Oh, we are nowhere near. Okay, okay. In older code, you may see two other letter types used instead of null pointer. The first is the literal zero. Okay, I'm just going to speed things up. Okay, there's null pointer. For example, don't show this. For example, only don't do this. Yeah. Okay. Cool. So this will work. What is initialize? What is zero? Return zero as an aside. On modern architectures, the address zero is typically used to represent a null pointer. However, this value is not guaranteed by the C++ standard, and some architectures use other values. The literal zero, when used in this context of a null pointer, will be translated into whatever address of architecture used to represent a null pointer. Additionally, there is a preprocessor macro called null, defined in the C_std_def header. This macro is inherited from C, where it is commonly used to indicate a null pointer. Sorry. Um, C standard definitions. Yeah. Double pointer, pointer null, pointer. Okay, this and this. Return zero. Both zero and null should be avoided in modern C++. Use a null pointer instead. Yeah, pass by address. We discussed by in lesson 12.11. Yeah, cool. 12.11. Oh, it's in the upcoming lessons. Yeah. Uh, Favor references over pointers whenever possible. Pointers and references both give us the ability to access some other object indirectly. Pointers, okay, sorry. Pointers have the additional abilities to being able to change why they are pointing at and to be pointed at null. However, these pointers abilities are also inherently dangerous. A null pointer runs the risk of being rereferenced and the ability to change what a pointer pointing at, creating a dangling pointer is easier. So int main pointer null pointer int x this address int is destroyed, the pointer is still pointing at that memory address. If pointer this, this will run, right? If pointer is true, it will point undefined behavior. Yeah. So I'm going to run this code and I'm still going to get the value 5. Watch. Let's see. Oh, yeah. Since references can't be bound to null, we don't have to worry about null references. And because references must be bound to a valid object upon creation and they cannot be reseated, dangling references are harder to create. Because they are safer, references should be favored over pointers unless the additional capabilities provided by the pointers are required. What was the additional stuff? Be able to change at they're pointing at and to be pointed at null. Yeah. Since references can't be bound to null, not so safe. Because they are safer, references should be favored over pointers unless the additional capabilities, yeah. Favor references over pointers unless the additional capabilities provided over a joke. This is what I've been doing this stuff for. Did you hear the joke about the null pointer? That's okay. You wouldn't get the reference. Uh, oh boy. That's okay. You wouldn't get the reference. The reference. The reference. You know. There should be there should be so this will look cool. This looks better. Quiz time. Okay, that's a good joke. I'm going to send this to a couple of my friends. Okay. Quiz time. Question one, can we determine whether a pointer is a null pointer or not? If so, how? Can we determine whether a pointer is a null pointer? Yeah, if condition or implicitly let it convert implicitly to a Boolean value. So if the identifier of the pointer, whatever convert to Boolean value, yeah, that's what I was telling you. Can we determine whether a non-null pointer is valid or dangling? If so, how? We cannot. We cannot be sure whether it is dangling. Yep. For each subitem, answer whether the action prescribed will result in a behavior that is predictable, undefined, or possibly undefined. If the answer is possibly undefined, clarify when. Assume that any objects are mentioned are of a type that a pointer can point to. Okay, let's do this. We need to get every single one of these correct because I'm the champion in pointers. Okay, pointer is in my veins. Okay, do not mess with me. Okay, assigning the address of an object to a non-const pointer. Hmm, it is allowed. Oh, I was supposed to say predictable, undefined, and possibly undefined. Okay, okay. This just copies the address into the pointer object. Yeah, cool. Assigning null pointer to a pointer. That is allowed. Dereferencing a pointer to a valid object. That is, we know the object is valid. Okay, so that is allowed. Cool. Dereferencing a dangling pointer. That is undefined behavior. Well, technically it is possibly undefined because the object might be overwritten or not, depending how the compiler is doing the stuff. But I know the answer for what learn CPP wants, so it's undefined. Cool. Dereferencing a null pointer, that is surely undefined. Boom. Dereferencing a non-null pointer, it can be dangling or the defense can non-null pointer if the pointer is dangling. Yeah. Why should we set pointers that aren't pointing to valid object to null pointer? Because we set pointers that are pointing to valid object because we don't want to leave them dangling. So we can easily add a conditional. So we can check like the pointer is not something that is invalid. Whether valid, yeah, same basic. Boom, escape. Okay, new stuff. How big is it? Pointers and const. Pretty small. Let's do it. 1 hour, 1 minute in. Okay, let me check one thing. Just a minute. Boy, what is happening to this? Okay, so pointers and const. Okay, consider the following code snippet. X pointer y this pointer 7. We can change the value of the address being held. Yeah, yeah, pointer this 3 points to 6 now. 6 is 7. Yeah, okay. So the value at y it's now 7, which you will say that it should not be possible because that is very risky. So we should make it const instead. Is that what you're saying? With normal non-const pointers, you can change both what the pointer is pointing at by assigning the pointer a new address to hold or change the value of the address. Oh, nice. I think they are going to discuss this, but I'm still going to, confirm that myself. Yeah, let's try that. So what I was going to try is, so if I do int a10, cool, and then if I do, what is it? What was I going to do? Oh yeah, const. Yeah. So const int pointer b is equal to address of a. Okay, that's cool. And then is this valid? Oh, okay. So now if I'm try to modify this, so let's say I do int c, which is also 5, and definitely I can't do this, right? B is equal to and of c. So I should get an error over here. What? It worked? Wait, what? Huh? 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 This is const int pointer. What are you talking about? Boom. How is that possible? What? What? Then what's the use? Okay, now you get an error. So const int pointer allows the changing of the pointer, like the uh, what it is pointing at, but it isn't allowing the change of the value of the integer. I'm just bad at explaining. I'm so sorry, guys. With normal non-const pointer, we can change by assigning a new value to the dereference pointer. However, what happens if the value we want to point at is const. So this is const. Well, then we can't. Compiler cannot convert from const int pointer. Oh, okay. Compiler cannot convert from const int pointer this to int pointer. So this should needs to be const too. Okay. So if I do this, oh wait, let me keep this. So if I do const int x 11, and if I do const int pointer y, which is actually address of x, so this is valid. Yup, but if this is not const, then I get an error. Yup, a variable of type int pointer with an r value of type const int. Yep. So this is R value, as we said. It will convert to R value. The above snippet would compile. We can't set a normal pointer to a pointer, a normal pointer to a point at a const variable. This makes sense. A const variable is one whose value cannot be changed. Allowing the program to set a non-const pointer to a const non-const value would allow the programmer to dereference the pointer and change the value. Yeah, which is against the rules of the constness. Yeah, okay, they also mentioned that. Pointer to a const value. A pointer to a const value, sometimes called a pointer to a const. Okay, a pointer to a const value, sometimes called a pointer to const for short, is a non-const pointer that points to confused. Let's read that again. A pointer to a const value, sometimes called a pointer to const for short, is a non-const point. Is a pointer that points to constant value. Okay, so this is valid, valid. Okay, cool, not allowed. To declare a pointer to a const value, use the const keyword before the pointer's data type. In the above example, pointer points to a constant because the data type being pointed to is const. The value being pointed to can't be changed. However, because the pointer to const is not const itself, however, because the pointer to const is not const itself, it just points to a const value. They can change what the pointer is pointing at. Confused. Okay. However, because a pointer to const is not const itself, it just points to a const value. We can't change what the pointer is. Oh, okay, got it. What the pointer is pointing at by sending the value new address. Okay. Pointer points to const int x. Cool. Uh, Pointer is equal to and y. Okay. Pointer now points at const int y. Yeah. Oh, that's what we are looking at. This is allowed. Just like a reference to const, a pointer to const can point to non-const variables too. A pointer to const treats the value being pointed to as constant, regardless of whether the object and the address was initially defined as const or not. Sorry, really sorry. So yeah, x is non-const. This is allowed. Pointer points to const int. Yeah, this is not allowed, but this is allowed. Const pointers. They can also make a pointer itself constant. A constant pointer is ah, ah okay, okie dokie. Cool, cool. Const after the asterisk means this is a constant. This is a const. Okay, cannot be changed after initialization. It declares a constant const pointer. Use the const keyword after the asterisk in the pointer declaration. Cool. In the above case, pointer is a const pointer to a non-const int value. Just like the normal const. Okay, so I should not be allowed to do this, right? Okay, so let me try. So if I was over here and I have const over here, so now let's try dereferencing what is already present inside B. 6. Is this allowed? Yep, that is allowed. Yep, that is allowed. But, oh, sorry, this is not allowed. Yeah, let's go. Uh, Yeah, just like a normal const variable, a const pointer must be initialized upon definition, and this value cannot be changed via assignment. Cool. Int x y, phi 6, int pointer, const pointer, and x. Okay, so yeah, this is the constant pointer, its address is defined. We can do this. Wait, int pointer, pointer, and x. Okay, the const pointer is initialized to the address of x. It was initialized already, so it cannot be changed. Boom, not possible. No, not allowed. No, not allowed. However, we can because the value being pointed to is non-const, it is possible to change the value being pointed to via dereferencing the const pointer. Yeah, this is allowed. Const pointer to const value. Oh, finally, it is possible to declare a const pointer to a const value by using the const keyword both before and after. This is the most horrible syntax that I ever see. My God, a const pointer to a const value. Yeah, cool. A const pointer to a const value cannot. Okay, I need to understand what Rust does. Okay, how do different languages handle this? Okay, shut up. Oh, shut the fuck. Okay, my earphones are going to turn off. 20%. Okay, fine. I need to somehow complete some stuff over here. Okay, pointer and const. Okay, not value it is pointing to can be changed to the pointer. It can only reference to. Okay, pointer and const recap. Yeah, I know most of the stuff. Yes, fine. Yeah, okay. Non-const can be. Yeah, okay. I remember most of the stuff. That's fine. Is there a test? No, that's not a test. Skip pass by address. So this is pretty big. So I think I'll stop the video over here. Uh, just give me a minute. Back again. So pass by address. I think this is pretty big. So this might take some time. If I go to table of contents, we have reached over here. Pass by address. So we only covered three chapters today. Two, I guess. Okay, this is getting a bit out of hand, but okay. So we covered about pointers, right? Pointers, null pointers, pointers, and calls. Sure. Three chapters. So three chapters. So okay. I guess in the next video I'll try to cover one, two, three, maybe three chapters, and then we will leave out three chapters for the next video. How about that? So I guess okay. Thanks for watching this video. I might record the next video right now itself, but my uh, the like the earphones, they don't have any charge left, like much of the charge. I can hear them, like this still looks 20%, but it's not. I can hear the tudung again and again, like the ringing. So they are dying out. I need to charge them, but I might record the video right now itself, like after maybe 15 or 20 minutes. So okay, thanks for watching this video. I'm Aditya Bashani, and I am an engineer for fun. Bye.